Let's now think about what it means to add and subtract complex numbers. So let's say I have a complex number a, and let's say that it's equal to 3 plus 2i. And let's say I have complex number b that is equal to -1 minus 3i. Let's think about what it means to add a and b. So let's say I have a third complex number that is c, that is defined as a plus b. So I encourage you to pause this video and think about it on your own what a plus b is going to be. Well, what we could do is, this is just going to be equal to, 3 plus 2i, that's a, 3 plus 2i plus b, which is, so plus -1 minus 3i. We could write it like that if we want to really be clear what b is and what a is, just like that. Now, how would we actually add these two together? Well, we can't add a real part to a complex part. That's why this is about as simplified, or we can't add a real part to an imaginary part, I should say. That's why this is about as simplified as you can get. But I can add real part to real part and imaginary part to imaginary part. So I could add the 3 to the -1 to get 3 plus -1 is 2. So I get a real part now of 2. And then I can add the two imaginary parts. So if I have 2i minus 3i, 2i minus 3i, that's going to be -1i, or I could say that's going to be -i. So just like that, I added the two real parts, added the two imaginary parts, and I got 2 minus I. And we could also visualize this on the complex plane. We could do that using an Argand diagram. In an Argand diagram, we represent each of these complex numbers as vectors on the complex plane. So that's our imaginary axis. This is our real axis. And a is 3 plus 2i. So 1, 2, 3 along the real axis, and then 2 along the imaginary axis. The imaginary part is 2i. So 3 plus 2i gets us right over there. And I'm going to represent that as a vector. Where its tail is at the origin and its head is at the coordinates 3 on the real axis, 2 on the imaginary axis. So that right there on my Argand diagram is my representation of vector A. Now let's do the same thing for vector B. It is -1 along the real axis and -3 along the imaginary axis. 1, 2, 3. So it sticks us right over there. If we represent it as a vector or complex number B could be visualized this way. And now when we add A plus B, you could add them the exact same way that you would add vectors. You take the tail of B, or you essentially shift B over. So you take the tail of B and you put it at the head of A, but it's the same thing. So when you go down 3 and you go to the left 1. So you go down 3 and you go to the left 1. So it's going to put you right over here. So all I've done is I've shifted B over to this part so that its tail is at the head of A. So it goes right over there. So this is vector B, or not vector, this is complex number B. So this is B right over here. And notice, now if we start at the tail of A and we go to the head of this shifted B, this right over here is going to be vector C. This is going to be A plus B. So this vector right over here, C, notice C is 2 minus I. 2 real part, -1 imaginary part. This right over here is C, which is A plus B. So you were able to add these two complex numbers. You could visualize adding them the same way that you would visualize adding when we added two vectors in the traditional coordinate plane. And it makes complete sense because this is when you're adding these complex numbers, you're keeping the real part separate, and these are essentially the horizontal components of the vector, and you're keeping the imaginary part separate, and that's essentially the vertical parts of these vectors.